Another Stokes theorem example, we're asked to find the flux of the curl of f. And when you see that curl in there in a flux integral in a surface integral of a vector field, that's a good indication that you might want to think about Stokes theorem. We are given an orientation for the surface, we're given the function to integrate, and we're given the surface itself. So let's start by thinking about that surface itself. The surface z equals 5 minus x squared minus y squared. We've dealt with these a lot at this point. This is a paraboloid. Okay. But it's only the section of the paraboloid above z equals 3, the plane z equals 3. So we're only dealing with the cap. I think it says cap in the description. So we're dealing with the cap of a paraboloid above a certain part. So that's a surface. We have an upward normal vector. So that's going to give us our orientation. And we want to find this surface integral. Now this is going to be hard to do. It's going to be, the surface integral, like any surface integral, is going to involve parametrizing the surface, finding the equation of the normal vector with a cross product, finding the parameter domain, setting up a double integral, doing a double integral. It might be doable here. The function we're integrating is kind of messy, but maybe possible. But it's not what we want to do. We want to try it as a line integral. So we're going to convert this to a line integral using Stokes. Stokes theorem. So what do we need in order to do that? We need to know the line itself. So to find the line, to find the curve, C, that's the boundary of our surface S. So the boundary of our surface S is this particular circle right here. How do we find the equation of that circle? We find the intersection of the two surfaces in question. Z equals 5 minus x squared minus y squared, and z equals 3. To find the intersection of those, we just set those equal to each other. So we have 3 equals 5 minus x squared minus y squared. In other words, x squared plus y squared equals 2. So it's a circle of radius 2 for C. Now, is C, what direction? Is it going to be counterclockwise or clockwise? That's going to affect our parametrization. And, well, with this outward normal, right, we draw the outward normal. Put yourself in the position of that arrow. Think of yourself as right there, and walk around the circle. In what direction, walking around the circle, do we keep the surface on our left-hand side? The surface is on our left if we walk around in this direction. So it's going to be counterclockwise, which is good because that's our standard parametrization. Square root of 2 cosine t, comma, square root of 2 sine t. And the z component for this circle is 3. Right? The circle is up there at height 3, so the z component for this circle is 3. That's tricky. We got to pay attention to that. We know for a line integral, for work integral, we need the derivative of this. So we take the derivative. There's our derivative. The actual line integral is going to be the integral from 0 to 2 pi. That was our parameter domain to go one time around this full circle. The function that we are integrating, oh, this is a mistake. This is supposed to be the curl of f right here. The curl of f is given in the problem, not f itself. My mistake. So the curl of f is negative x times z. So let's see what we've got. F, or I just lied. That's f itself. It's not the curl of f. We don't have to take the curl of this because we're doing it as a line integral instead of as a surface integral. Sorry. Feel embarrassed, but mistakes happen. There we go. So there's f for reference. Let's see. The first component of f is negative x times z. We want the values on the curve that we're integrating on. On the curve, x is root 2 cosine t, and z is 3. So this is going to be negative 3 root 2 cosine t, comma, y times z is 3 root 2 sine t, and then x times y times e to the z looks like x times y is 2 cosine t sine t, and then e cubed, e to the z. Now we want that dotted with r prime, so we want that to be dotted with minus root 2 sine t, comma root 2 cosine t, comma 0 dt. This thing I put in there kind of got in the way, but I needed it as a reference. So let's take that dot product. Root 2 times root 2 is 4. 4 times 3 is 12. Negative times negative makes it a positive. Cosine t, 12 cosine t sine t, plus, let's see, same story, 12 cosine t sine t, plus 0, happy to have that 0 there, dt, and we end up with the integral from 0 to 2 pi of 24 cosine t sine t dt. We can do this with a u substitution. U equals sine of t, du is cosine t dt. This becomes the integral from t equals 0 to t equals 2 pi of 24 u du. So that's 12u squared over 2. The 2 canceled in the 24 to give us the 12, which is 12 sine squared of t from t equals 0 to 2 pi. Sine of 2 pi is 0, sine of 0 is 0. This all integrates to 0. You'll be surprised how many of my math lab problems have 0 as an answer. So there it is. This was a problem that we didn't want to do as a surface integral because we would have to take the curl of it, figure out the surface parameterization, normal vector. As a line integral, though, it wasn't that bad, right? It worked out pretty well as a line integral, and that's an example where we want to use Stokes' theorem. In particular, we want to pay attention when we're asked to find the flux of the curl of f. If it's curl of f in there, not just f, that should trigger in our minds prompt to think about Stokes' theorem. Think about using it and applying it to do a line integral instead of a surface integral.